All right, so let's jump into the definitions at the beginning of Book 1 of Newton's Principia. This is from Chapter 19 of A Student's Guide Through the Great Physics Texts. The first definition that Newton provides is for what he calls quantity of matter. So I'll write this out. Definition 1, he defines quantity of matter. And what does he mean by quantity of matter? Well, he says that he means the measure of matter. How much matter there is. By quantity of matter, he means the measure of matter. It's basically how much stuff there is there. How much stuff there is there. We would call this nowadays, we would call this mass. The reason he doesn't use the term mass, he uses this term quantity of matter, is because the word mass was already being used colloquially just to mean just like a bunch of stuff, right? And he wants to be a little bit more scientific, so he doesn't use the common word mass, like there's a big mass of potatoes over there. He says quantity of matter in a more scientific way. And in particular, he mentions that the quantity of matter is formed conjunctly by the density and the bulk. So how would we express this? Well, if we talked about mass as m, I'm going to write down a formula here. If you want to compare the quantity of matter in two objects, the quantity of matter in object 1 and the quantity of matter in object 2, you have to compare both the densities of those two objects, and you have to compare their bulks or their volumes. So this is how he's thinking about that. If you want to compare how much quantity of matter, or we would say mass, are in two objects, you have to compare the ratio of their densities, and you have to compare their bulks or their volumes. And again, here is what we would call mass, but he would call quantity of matter. I will probably just use the word mass. Okay, so there you have it. If you don't like forming these kind of ratios, of course, you can write it as just an equation, mass equals density times volume. You're probably familiar with this formula anyway, but this is a way of saying how much mass is there compared to, for example, a standard kilogram. Okay, so that is Newton's first definition. His second definition, definition 2, is quantity of motion. Quantity of motion, and we should emphasize by quantity of motion, he means a measure of the motion. How do you measure how much motion something has? So how much motion a thing has. This is what we today would call the momentum of an object. And I will probably use the modern terms, but it's good to keep in mind that he's referring to it as quantity of motion, or sometimes just as motion. By that, he means the momentum of an object. And he says, how do you compare the quantity of motion, or the momentum, of two different objects? If we call the letter P the momentum, you can compare the momenta of two different objects by comparing their masses, or their quantities of matter, and their velocities. Okay, so the ratio of the masses of the objects and the velocities of the objects. And these would be the momenta of the objects. And once again, if you don't like forming these ratios, you could just say the momentum of an object is equal to its mass times its velocity. Okay, so these are a couple of important formulas And really, so the formulas on the right are probably how you're used to seeing these kind of quantities written, but this is how he was writing it as a ratio or a comparison of these things. Okay. What about definition 3? We can probably get through definition 3 and then I'll probably take a break. So definition 3 is vis insita, or the innate force of matter. The innate force of matter. What do we mean by vis insita, or the innate force of matter? He describes it as a power of resistance to changes in the present state of motion or rest. So I'll write that down. So something's vis insita is its power of resisting changes in its present state of motion or rest. This is what we today would call the inertia of an object. And the inertia of an object can manifest itself, Newton says, as either resistance or impulse. So I'll write this down. It manifests itself as either resistance or impulse. So what do we mean by this? Well, he says if a body is at rest, then inertia shows up as resistance. Shows up or manifests itself as resistance. If it's at rest, it shows up as a resistance to an impressed force that's acting on the object. I'm going to put this in quotation marks, an impressed force acting on it. So for example, if you have a dresser in your bedroom, it has inertia. It has a power of resisting changes in its present state of motion. So if your dresser is at rest in your room and you try to push it, it resists that impressed force acting on it. It's hard to move it. So the inertia is showing up as this resistance to moving. But if a body is already in motion, then its inertia shows up as impulse. Its inertia manifests itself or shows up as impulse. What do we mean by that? It's an impulse that is able to deliver, that it is able to deliver to another body. Okay, so for example, your car, when it's driving down the road, it has inertia. So it's going to resist changes to its present state of motion or rest, right? And this car, because it's in motion, when it strikes something else, its inertia shows up as its ability to deliver an impulse to something else that it hits. So if it runs into, God forbid, a parked car, it delivers an impulse. It applies a force to that other object that it strikes. Okay, so inertia kind of has two ways of showing up, and one of the things that Newton is emphasizing here is that the state of rest and the state of motion are relative quantities. Something that's at rest compared to one person might be in motion compared to another person. So for example, if you are driving in a car, the car is really at rest compared to you, but if you're standing alongside the road, that same car is in motion compared to you. So he's kind of getting us to think about this right away. But in either case, although motion and rest are relative quantities, the fact that this object has inertia is not relative. It simply has inertia by virtue of the fact that it has mass.